This video is an introduction for physics to the ideas of free fall. You've already learned about motion equations, and we've applied those where we list our 5 variables, we fill out 3, the picture, which way is positive, all that. Now you're going to apply those to some problems that are in the vertical, in particular what we're going to call free fall problems. When we have a problem that we can consider to be in free fall, we can then know the acceleration in the vertical direction. The idea of free fall is that we're going to neglect all the forces acting on the object except for one, gravity. So if the only thing acting on the object is gravity, that force of gravity pulling down towards the center of the earth, we can then apply the ideas we're going to talk about here today for free fall. Okay? And sometimes that's a really good approximation. Like if I would drop Mario Ball from this height here, it's a pretty good approximation that he was in free fall the whole time. If I drop Mario Ball off the Empire State Building, at some point free fall will not be true. Okay? In fact, you're going to learn about terminal velocity. At some point he'll reach terminal velocity and have an acceleration of 0. But we're going to focus today on, if we're neglecting things like air resistance and just focusing on the effect of gravity, that's going to be our free fall problems. A couple examples of this. So I could toss Mario up in the air like that. I could drop him, or I could throw him down. In all of those cases, from the moment he leaves my hand, not when he's in my hand, that's a different type of problem. We'll get some different tools in our toolbox to deal with that later, throwing and catching things. Okay? But from the moment he leaves my hand until the moment right before or as he hits, he's in free fall. Same thing for me throwing him down. From the moment he leaves my hand to the moment right before he hits my hand or the ground down below, Mario Ball is in free fall if we're neglecting air resistance. Okay? So this is while he's in the air, not when he's in the person's hand or having the collision with the ground. Those collision problems and those throwing problems, we'll get to that eventually. Okay? And that acceleration, if we're in free fall, in the y direction, this is up and down in the y direction, will have a magnitude of 9.8 meters per second squared. So that's the size of it. And if you call up positive, which we'll typically do on our problems, that acceleration due to gravity is always downward. That's true for this one, and for this one where I drop it, for the one where I throw it up, and for the one where I throw Mario Ball down. In all of those cases, while he's in the air, the entire time he's in the air, if you call up positive, you can use an overall acceleration in the y direction of negative 9.8 meters per second squared. And when we're doing our problems, our initial problems, you may assume free fall. If you're ever not sure if you can assume free fall, simply ask. On our first test, you will be able to assume any of the projectile problems are in free fall. Okay? So that's the acceleration we get to use. That's the new piece of information. So now a couple of things to help you solve the problems. You get to decide when the problem starts and ends. So let's say we were on a cliff and we threw Mario Ball up in the air and he did something like this. And then there's right before he hits. Okay? Now, if I throw him straight upward, okay, there wouldn't be any of this little bit of parabola that I have here. It would just go straight up and straight down. But for clarity, in terms of being able to visualize this, I've spaced it out so it doesn't overlap. So think about Mario Ball going up. Imagine here's a cliff. Mario Ball goes up, and then he goes down and then hits the ground down below. That's the idea that I'm trying to express with this picture, so we can talk about it and I can point to some stuff here. So when you're solving these problems, you get to decide when you start the problem and you get to decide when you finish the problem. What do I mean by that? Well, let me list my 5 variables here. Notice how I'm using a y because we're in the vertical direction. Go ahead and list these. And t. Okay. You get to decide what the spot is to start the problem, which can have an effect on this, and it can have an effect on this, and it can even have an effect on this. We've already talked about this one. For all these problems, if you're calling up positive, you'll get to put in a negative 9.8 meters per second squared right there. Okay? But these guys, okay, you can, and it'll affect this as well. But these guys, especially V initial, V final, you get to decide when is the initial velocity, when is the final velocity. The only thing you have to know is that the final has to come after the initial for the motion equations to work. Okay? So what does that mean? Well, if I asked you how high Mario Ball went, okay, in this example where he's thrown upward, and I gave you some other information as well, you'd start the problem right here, and you'd stop the problem right there. Okay, so you wouldn't go all the way to when he hits the ground. You would just go from here to right here. And this would represent your v initial y, whatever value you had at that spot. And this would represent your v final y. Maybe you care about how long he's in the air, the hang time of Mario Ball. Well, now this would be a v initial y. This would not be v final y anymore. We'd be talking about down here somewhere, and the corresponding displacement to go with that. Okay? So you get to decide when the problem starts and when the problem ends. Just make sure that the final velocity is after the initial velocity when you're thinking about it, or that your displacement is for the part of the trip that you're thinking about. If I'm looking for that first one again, how high he goes, I'd be looking for that, and that would be the displacement I would use. If I'm looking at the hang time one that we talked about, the time to hit the ground, I would look at a displacement and I would be using this. More on that in just a sec, but it would be, here's my initial position, here's my final position, because this is a change in position, final minus initial. Okay? So it would be end up being this value right here with the correct direction. I want to show you a few things to look out for, or a few ideas that will help you fill out the 5 variables. And the first one is, when you toss something up in the air like this, when it switches directions, and this is true for any one-dimensional problem, okay? When an object switches directions, if you can only travel one way or the other, it has to come to a stop. If you were in your car going that way, 50 miles per hour, and I said you can only drive in a straight line, and you need to go the other way, you'd have to slow down, come to a stop, and then start going the other way. Same thing is the case here. So what does that tell us? At the highest point, the velocity of Mario Ball in this vertical direction is 0. So sometimes, if you're looking at something for maximum height or time to the highest point, you'll get to put a 0 in for v final y, because you'll go from where it starts to the highest point. So that's the first thing. Okay? The next thing is for v initial. If the object is dropped, first, this goes back to our dropping activity. For a split second, when I let go of Mario Ball, he's at rest, and then he goes faster and faster down. So for a split second, he's at rest. So sometimes, if you have something that is dropped, your initial velocity in the y could be 0. That could happen. All right. Or another option is, let's say you start your problem at the highest point, and that becomes your initial. Well, at the highest point, the initial velocity would then be 0. We don't typically do that for our problems, but you could. You could. All right. And now let's talk about displacement. Let me just act this one out. So let's say we were doing a problem like this. Again, like that. What's the displacement overall for the whole trip if you were looking at the whole thing? Well, he goes up, let's say, I don't know, half a meter. He comes down half a meter. He's back where he started. That's a displacement of 0. So sometimes there can be some symmetry in the problem, and if the object is back where it started in the vertical direction, your displacement in the y direction, you get to write a 0. You get to write a 0. Now what about if that's not the case? Let's go back now to our little cliff example here, where I had Mario Ball doing that kind of thing. Okay? And let's say the cliff is, I don't know, 12 meters tall. So if we have this type of scenario, and we're looking at this being the initial and this being the final. Maybe we're looking for the time it's in the air, or maybe we're trying to solve for that v final y, final velocity there right before it hits the ground, going down. You could use a displacement here of negative 12 meters. Couple of ways to wrap your head around why that's the case. Okay? One, simply point. Where did he start? Where did he finish? And then think about drawing an arrow. If I point here and here and I draw an arrow, that arrow would be 12 meters going down. Since up is positive, negative 12 meters. So that's one way to think about it. Another way to think about it is, here's the cliff again. Mario Ball goes up. Okay, let's call that, I don't know, 0.2 meters or something. And then he comes down 0.2 meters. At this point, he has a displacement of 0. And then he goes down 12 more. So down 12 more means our change in position or our displacement would be negative 12 meters. Number one mistake on tests with cliff problems is with this. Okay, think about which way it went overall, and then you should be comparing that idea to which way you've called positive. Okay? As long as you call it positive and you're on a cliff, and you're looking at the time till it takes to hit the ground, or the final velocity right before it hits the ground, you'll be putting a negative on there if you've called up positive. All right, so what happens if you fill out 3 of these and you pick an equation, for example, like this, and you end up with a t and a t squared. So in other words, there's initial velocity and there's this acceleration of negative 9.8. You're not going to be able to factor these. Okay? These are not designed to be factored. So what do you do when you've got a t and a t squared? Well, What do you do in math class when you have an x and an x squared? Quadratic formula? Great. If you want to do the quadratic formula, x equals negative b plus minus square root of b squared minus 4a, you know, that whole thing, go for it, okay? Or, I don't recommend doing that, or graph it, okay? Figure out, make it so that 0 is on one side and everything's on the other, and then graph it and find where your intercepts are. And wherever you've got your y value of 0, that'll be your answer for your time. If you know what I'm talking about, great, do that, especially if you have a graphing calculator. If you have no idea right now what I'm talking about, don't do that. I'm going to tell you something else to do instead. The other option, okay, if you're looking for time and you end up with that equation and you filled out v initial and displacement and acceleration. Those are all numbers from over here, okay? So pretend we have the v initial and you'd be filling that out, trying to solve for time, not caring about v final. There's another way you could do this. Instead of, if you get here and you're like, I don't want to do that math, okay, what you do is solve for the one you don't care about. Go ahead and solve for v final y. And it will not be 0 because you're looking at the whole time it's in the air for this one I've done. It's not the highest point or anything like that, okay? So go ahead and solve for v final y. Now you know 4 of these things. Pick any equation you want now, except for that one, that has time in it, and you won't need any extra math. It'll just be Algebra 1 stuff again. So the way around it, the quadratic formula or the graphing, is to simply solve for the variable you don't care about, okay, if you realize you're going to need the quadratic formula. Then you know 4 things. Pick an equation with time in it that's not this one, and you'll be able to directly solve for t. So no quadratic formula, no graphing and finding the intercepts where the y values are 0. Just the stuff we've already done, So that's what I recommend if you're not comfortable with either quadratic formula or this. Also, on test day, I'll let you know that if this is the equation that ends up getting used on a problem, and this will be for all our tests, it'll only be worth 1/4 of a point on a test that's at least 100 points. Okay, so a test that's at least 100 points, this will be 0.25% of the grade to go from here to the answer. Okay, so if you're going to do the quadratic formula, it's going to take you 10 minutes or whatever. Do that at the end. Get everything else done in the test first, including the bonus. So I'm going to go ahead and now do a real quick setup for a problem. So let's go ahead and make this into a free fall problem here. And I'm going to say the words. You're going to have, I think, 4 or 5 problems you're going to practice in class. If you haven't already tried some of them, you should be watching this first. But I'm going to go ahead and say the words. So we're going to say Mario Ball is on top of a 15-meter cliff, and he is, I don't know what happened to his face there, and he is launched upwards at 3 meters per second. So Mario Ball, the problem would say something like, Mario Ball is on top of a 15-meter cliff, he's thrown upward or launched upward at 3 meters per second. And there's a lot of stuff that I could ask you. For this one, I'm just going to figure out how fast is he going when he hits the ground? And the answer is not 0. Okay? Because remember, we're looking at these problems while the object is still technically in the air. So it's the moment from when I let go to the moment before or the moment as he hits. If I ever say, find the velocity when he hits the ground, the answer is not 0. It's some big number going down. Okay? So how fast, in this case I'm saying how fast, is he going when he hits the ground? Going when he hits the ground. All right, so what are we going to do? We're going to draw a picture. We've already done that. We're going to define which way is positive. I'm going to go ahead and call up positive. That's what most of us do. Then we're going to list our 5 variables for the y direction. Okay, and we're going to try to figure this out. So let's go ahead and list our 5 variables, y minus y naught. And in no particular order. You can make these whatever order you want. V initial y, or v naught y, v final y, and time. Oops. Didn't want to put a question mark there yet. Okay, so let's try to fill some stuff out. Let's start there with displacement. Do we know the displacement? Yeah, because what's he going to do? He's going to go up and then come back down. So imagine the cliff's here. He's going to go up, and then he's going to keep on going down. How much is he going to go down? He's going to go down overall 15 meters. So negative 15 meters. There we go. Negative 15 meters. It's just a little messy. Still a little messy. Let's clean that up. Okay, someone's trying to pause and take a screenshot. All right, so we got negative 15 meters because he starts here and he's going to finish down here. Okay, and we're trying to figure out how fast he's going when he hits the ground. So my starting point is when I first release, and my finishing point is right there, right before he hits the ground. Acceleration of the y, we're going to assume free fall. So since I called up positive, acceleration due to gravity is down towards the center of the Earth. So negative 9.8 meters per second squared. Initial velocity in the y, I said he was launched upward at 3 meters per second, so this is positive 3. If he had been thrown downward, we would have put a negative on there. If he was dropped, we would have put a 0 in for that. And that's it. Those are the only types of problems I can give you off a cliff. Either he's dropped, thrown upward, or thrown downward. That's it. Okay? And then v final y, that's what we're trying to find. And we don't care about time. We don't care about time. So I'm going to pick the equation that doesn't have time in it. And let's go ahead and do this over here. V final squared equals v naught squared plus 2a y minus y naught. Everybody can see that, yeah. All right. And I'm going to put some y's on here because eventually we're going to do problems that are in the x and y direction. If you don't have y's on all of these on the first test, it's fine. And even technically, if you have an x minus x naught here, I'll still give you credit on the first test. But very soon, you're going to have use the x and the y's. Okay? I shouldn't say very soon, eventually. So let me go ahead and plug in the values here now. V initial y is 3 meters per second. Square it, plus 2 times negative 9.8 meters per second squared times negative 15 meters. All right. So we've got a squared here. Quick math review. If I had x squared equals 4, how would you solve that? What would you do? Square root of both sides. Now, when you do that, what do you have to write for your answer? What do you have to do? Add a plus or minus in math class, right? Because there's two solutions here. Because when I take the square root of both sides, over here I get x. And over here, if I don't put the plus or minus, I'll lose the solution. In physics class, you pick one, okay? When we're talking about vectors. Because either when we're talking about a vector or a component of a vector, it's going to have a direction. So it's either positive or negative. Let's get rid of our little math review there. And I'm going to skip the algebra here. So we've got, let me grab my calculator real quick. Oh, you can also use 10 instead of 9.8 if you want for acceleration of gravity. If you're ever without a calculator, that's okay. All right, that plus 9, that to the half power. All right, so I would get in math class plus or minus 17.4. In physics, I'm going to pick my final velocity, and since I'm writing final velocity, I'm going to go ahead and do this. More than that in just a sec. My final velocity in the y direction is 17.4 meters per second going down. It's certainly not 0. If you ever think that it's 0 right before it hits the ground, think about what Mario Ball would do. He would go up, and then right before it hits the ground, he would hover. That's not what happens, right? It's still moving down when it hits the ground. Pretty fast in this case, okay? Now, the question said how fast. It did not say find the final velocity. So what do? Just take the absolute value. Drop the information on the sign or the direction of the vector. So my final answer will just be 17.4 meters per second. That's it. If you have questions, let me know next time I see you in class. There are other sample freefall problems that are in the Ed Puzzle playlist this year. They're also elsewhere on the YouTube channel.